Hi guys, welcome to today's video. We are just going to go through some more organic chemistry for NCEA level 3. So we're just going to go through some of the common experiment techniques. So I've got some diagrams here. Just want to highlight some of the key points that you need to know for the sake of the assessments, and just some really and just quickly go through how they work. Okay, and then we're going to go through some of the distinguishing tests. So this is including all the all of the common distinguishing tests for the different organic function groups. So let's get into it. And again, if you don't know this website, No Brain Too Small, so especially if you're a New Zealand student, surely you know this website. So if you need any assistance in any of the science subjects, this website is absolutely amazing with all the resources on the revision, on the questions, past exam questions, and everything else. It's just fantastic website. Please, if you want to give them full credit, because I've been using them in my teaching practice. I'm not getting paid by them or anything, but just sharing the this valuable resource for everyone. So if you're not sure where I'm getting this particular page from, that's from that website. Okay, so I'm just going to go through some of the experiments, that the techniques that you actually use in very not even just at high school, but at university as well. So I'll just go through just in the order. Let's just go through the order. So the separating funnel. So the funnel is a very useful thing, because it allows, because we know that in organic chemistry, the different function groups, some are soluble in polar substances, some aren't. Okay, so if we use water as an example, we'll talk about this in the distinguishing test as well. So if we look at the solubility in particular, so you got the likes of alkanes, alkenes, alkynes, and halalkanes, they don't dissolve in water. Whereas all the other functional groups, if you have a shorter chain of that particular functional group, like say for example an ester is a good example of fat. Fat doesn't really dissolve in water, but if you got the chain narrowed down to like 1 or 2 carbons, it can dissolve in water to a certain degree, but it's not a very good it's not going to dissolve. Okay, so you got ester, halalkanes, not soluble in water, would not mix with aqueous layer. So what it simply means is that if you have got 2 organic functional groups in this funnel, so you're looking at this funnel, all right. So if you got 2 substances with different polarity, with different solubility, if you mix them together, the dense liquid will go to the bottom, the other one will go on top. Like say for example, if you think about oil mixing with water, the oil sits on top of the water, and they won't mix. Okay, so what you can simply do, you can just control the filtering funnel, the separating funnel, and you can extract or separate, just to separate the layers, separate the mixture of 2 different organic compounds. Okay, so you just open the funnel, and then the less dense will stay on the top, and then the bottom layer, which is a denser part, will go into the speaker. So at the end of the day, if you just control your speaker, this part will contain one solution, and the other one will sit in the funnel. Okay, so which is like similar sort of thing of filtration in a way. Filtration is kind of like you're using drying agents. So whenever you see something anhydrous, just think of the wording, the English language. Hydrous means with water, anhydrous means without water. So you're using a drying agent to suck away all the water, and then this solid crystal thingy, this white powdery thing that sucked away all the water, will sit here in the filter funnel because it can't go through, and then everything else will run through. Okay, so the filtration method is not as common, but it definitely has its place its part. Now, distillation is set up like that. So we use this I talked about quite a lot during class. So we used it to separate mixtures that have got different boiling point. So the best example is you got alcohol, you got primary alcohol turn into aldehyde, and then which turns into carboxylic acid, right? And so your alcohol and your carboxylic acid all have hydrogen bonding, and when they have hydrogen bonding, they have high melting point and high boiling point as a result. But your poor aldehyde has no hydrogen bonding, and then because it has no hydrogen bonding, it's going to have a lower boiling point and melting point, so you can use that to separate the aldehyde as soon as it's produced. So what it means is that, let's say if this boils at 70 degrees, if this boils at 120 degrees, this boils at 50 degrees, for example, and then I'm going to heat up this solution here at, say, at 65 degrees Celsius, what's going to happen is that the alcohol won't evaporate. It's going to start reacting. The moment you make an aldehyde that has got a lower boiling point than the 65 degrees, it's going to vaporize. Where does it go? It's going to go up here, it's going to go through here, and then it's going to drip down here. So this condenser is going to make sure you have a constant flow of cool water surrounding the aldehyde, cooling it down, brings the temperature down, and then it's going to drop out as a liquid on the other side. Okay, and this works with anything really. If you got an impure mixture of things, if you know you got a mixture of 4 or 5 different substances in there, but if you know what they are, you can just literally change change the temperature of how much you're heating, and then you can get them out one at a time, and then that's a very, very common method. Now reflux, this is something that's, like I mentioned in class, you're going to probably do this so many times. Just recognize the picture, you won't need to draw this. So reflux is just you're just cranking up the heat as much as you can, and you just want to speed up the rate of reaction, and then nothing gets out of this container. So you can see this is all closed. This is a closed system, so anything that have got low boiling points, they want to evaporate, well, also known as volatile, they can't escape. Okay, so what you're just doing is that you just always increasing the heat, and then you have the condenser which is up here, so that's going to cool down any of the vapor that's went up and that's gone up to the condenser. It's going to cool it down and then just drops back down. So it's kind of like just you're just speeding up the rate reaction. Okay, so you're just making sure that the reaction goes to completion. Let's say, for example, I'm making A plus B turning to C, right? And then if you reflux, so what you're doing is that you increasing this rate of reaction. You want all the A's and B's to react to become C's in the less amount of time, because time is precious. Okay, so those are the 3 or 4 separate techniques. So you got filtration, you got separation, you got distillation, you got reflux, and then you got separation or extraction. Okay, so just be familiar with the diagrams, and sometimes they'll ask you why in this case we need to reflux. What is reflux? And with all the reactions, we'll talk about flowcharts in a bit, but most of the reactions requires concentrated H+. Okay, so if you do oxidation reaction, you use MnO4 minus H+, you got H+ here, and then if you do condensation reactions, you need acid, and you need acid and reflux. So you always have, most of the reactions that we learn, you always have a lot of H+ lying around in your solution, which is not very good because it makes it really acidic. Okay, so what we want to do is that we want to add a carbonate. So carbonate is something that's not the most reactive group of molecules, and not the most reactive thing. So normally you just chuck it into this mixture. The carbonate only has one job, is to find any H pluses, conc H2SO4s, if you have any unreacted carboxylic acid that you just simply don't want, any unreacted HCl in the preparation, whatever, it doesn't matter. You want this carbonate to go in there and get rid of them. Okay, so the carbonate is simply there to get rid of all the, it could be different scenarios as you could see, but I want them to get rid of H pluses. And how do you know the job is done? You no longer make bubbles. Okay, so that's a very common thing to do in the laboratory, because you don't want your solution to be very high concentrated with H2SO4. That means if you're reacting, if you need to do further reactions, or if you're handling it, it's not the best thing you want in the world. Okay, and then whenever you see this anhydrous salt, that just means you just want to get rid of any excess water. So we talked about hydrolysis, we talked about condensation reaction in class. So we're dealing with water quite often, and sometimes if we don't want any excess water in the thing, chuck in the anhydrous salt, and that's gonna get rid of them. Okay, so those are the experiment techniques. All right, so let's go through the distinguishing test. Okay, so we got the likes of the easiest one from year 12. So you got bromine water. Okay, so bromine water lets you do three functional groups. It gets rid of 3. So this is a test. This is test for saturation or unsaturation, whatever you want to call it. Okay, this is test for unsaturation. So you're looking to distinguish CC double bond, CC triple bond, and sometimes even just CC single bond. Okay, so this works with alkenes, alkynes, and alkanes. Okay, so with the bromine water, if you have an alkane, just CC single bond, it's going to do substitution reaction. And then what it does, you need UV light as a catalyst, and then this is going to go from orange to colorless in a few minutes. Okay, in a few minutes. Okay, now if you have a CC double bond, if you have a CC triple bond, so this is addition, this is addition. So what you're gonna get, you're gonna go from orange to colorless instantaneously, straight away. Okay, so this is a very, very good distinguishing test. Just knock out 3 functional groups out of the park. Okay, and then I'm just going to go through the easy ones first, and then you have the likes of Tollens reagent. So Tollens reagent only works with aldehydes. Okay, so Tollens only works with aldehyde because it turns the aldehyde into carboxylic acid with the Tollens. Because the Tollens is a very weak oxidant, so it can only oxidize aldehyde, because aldehyde is a really, really strong reductant. Okay, so what you're going to see, silver mirror. Okay, the production of silver. And the other thing that you can do to distinguish aldehydes is by using Fehling solution, or Fehling's reagent, or or Benedict solutions, or Fehling's, or you can use Benedict's. Same thing. What you're going to see, same thing, the aldehyde will turn into the carboxylic acid. Oops, carboxylic acid. And what you will find here, so this goes here, you're going to see the blue Cu2+, and then that will turn into red Cu2O precipitate. So because the active ingredients of Benedict solution and Fehling solution is Cu2+, and it will give you the red Cu2O. This looks ugly. So it will give you the Cu2O precipitate. Okay, so that's how you know you have an aldehyde. So the Tollens reagent and then the Fehling's Benedict solution only works with aldehyde. Okay, only aldehyde. It doesn't work with anything else because they're really, really poor oxidizing agents. And then you have the likes of litmus paper. So litmus paper let you distinguish your amines. Oops. So this distinguish the amines because this will go from red to blue because your amines alkaline. And then your carboxylic acid, obviously, is acidic. So this will go from blue to red because it's a what do you call it? It's a carboxylic acid. All right, and then you have acid chloride. Now, acid chloride, again, this is unique. The acid chloride itself, if you test it with litmus paper, it doesn't do anything. Okay, but the fume, you use litmus paper to test the fume, to test the product of the reaction, the HCl fume, and then that will go from blue to red. So if you just put, if you have a red litmus paper, if you just have a paper on its own, if you put in acid chloride, nothing will happen. But if you put moist, if you actually put moist litmus paper, and that will give you reaction, because moist means you got some water on it, and then the acid chloride will react with the moist blue litmus, and then that will turn red. Okay, so the litmus paper knocks out amine, carboxylic acid, and acid chloride. Okay, so that's how you can tell from those ones. And then we have, if you're just adding water as a reagent, if we're not looking at solubility, so reaction wise, it only reacts with acid chloride or acid chloride, same thing. Okay, so acid chloride plus water, this turns into your carboxylic acid, and this is a very, very exothermic reaction, very exothermic, and then you produce a white fume of HCl, which can be tested by litmus paper. So this is the only time that you can use water to actually do a chemical reaction with the organic functional group that we have. Okay, however, we can also use it to do solubility, because with solubility layers, so sometimes I've seen this in our school exam questions. They say put this in an aqueous something something solution. When it's saying that, that means in the solution there's lots of water. And when there's lots of water, you can actually compare the solubility. So if you think about the solubility, the haloalkanes, the hydrocarbons, so that's your alkanes, alkynes, your haloalkane, even your ester is not the best. Even sometimes the amide is kind of amide is more on this side. So these guys are more insoluble. Okay, so and then you got the likes of alcohol, amine, carboxylic acid, ketones, aldehydes, These things are, if they're short chained, and then they are most likely soluble. So that means so how does the insoluble and then the soluble part comes into play? So if you put this guy in water, if you put this in H2O, you will see 2 layers because they don't mix. If you put the soluble stuff in there, you will see 1 layer because it's, because they dissolve into one another. So that's what water does. Okay, so you can use water as a reaction with the with acid chloride, or you can do that with the solubility. And then there's that carbonate thing that we talked about. Carbonate works wonders with carboxylic acid, because carboxylic acid plus carbonate gives you salt, water, and CO2. Okay, because that's what we want. We want the bubbles. Okay, so the only thing that reacts with carboxylic acid, the only thing that reacts with carbonate in the year 12 and 13 syllabus is the carboxylic acid, because you see bubbles. It doesn't react with anything else. Okay, so so far we got the alkane, so the bromine water that eliminates your alkanes, alkynes. You got the carbonate to get rid of the acid. You got the litmus paper to get rid of the acid and amines. You got the solubility test with water. You got the water with the acid chloride. And then what about the primary, secondary, tertiary alcohols? Okay, so this is where I wouldn't recommend using, some people say, all right, so what if I use MnO4 minus H plus? All right, so or I can use Cr2O7 minus. Sure, this works, but it's not the easiest way to react. The reason being, the primary and secondary alcohols will react with this, and it reacts with that. It doesn't react with the tertiary alcohol, because tertiary alcohol can't be oxidized anymore, right? But then your primary alcohol turns into aldehyde, and then your secondary alcohol turns into ketone. So then you can technically say, okay, so my 2 products, and then I'll do the Tollens reagent. I can do Tollens, and then that eliminates, that will confirm which one's the aldehyde, which means that used to be the primary alcohol. And then the ketone doesn't react anymore. I mean, this could work, but it's 2 steps. All right, so and you should know that chemists and scientists in general are lazy. We don't want to do 2 steps when we can simply do 1. And this is where we introduce the Lucas test. So if you have a friend called Lucas, think of him. All right, Lucas test, which is using zinc. It's a mixture of zinc chloride with some concentrated HCl. Okay, so it just has a lot of chlorine. So this, with the Lucas test, using the Lucas reagent, the tertiary alcohol, you will have, you're gonna see rapid cloudiness. Okay, so the thing will become very cloudy instantly. the secondary alcohol in about 5 to 10 minutes, and then the primary alcohol no change. It doesn't do anything. Okay, so why does it go cloudy? Because the OH group has been substituted by the Cl group, and it's just much easier for the OH to leave when there are more hydrocarbons nearby. It's not something you need to consider in high school. So the Lucas test is something that's really handy if you have primary, secondary, tertiary alcohols. Or you can do the long way. You can just say, all right, so I can re-oxidize them with the MnO4 minus. What you're gonna see purple to colorless, and then with the Cl2O72 minus H plus, you can go from orange to green. Okay, so these are your typical color changes. And your tertiary alcohol doesn't do that. Okay, but then you have your products, your aldehydes, your ketone, and then you can distinguish them that way. Don't do it like this though. I've had someone telling me this. So if I use primary alcohol and I turn that into aldehyde, and then let's just say I'm using MnO4 minus H plus, then from an aldehyde I use MnO4 minus H plus, okay, and then I turn to carboxylic acid, and then the same person told me that, all right, my secondary alcohol does into MnO4 minus, turns into H plus, and then it makes a ketone, okay, and then this is what they told me. All right, so because I make carboxylic acid, this one's ketone, this one's acidic. So if I have got this beaker, okay, let's just say initially this is my primary alcohol, and I'm going to react with test tube, doesn't matter what it is. If I have my primary alcohol, I'm going to react it all the way to carboxylic acid, and then I'm going to put some litmus paper in this beaker, and then it should go red. And then they think they've done everything right, but this is wrong. Why is that wrong? Okay, why is that wrong? You got H plus here, you got H plus here, you got H plus here. So in your solution, you have got H plus as one of the ingredients, as one of the catalysts. So even with your ketone that's sitting in there, yes, the ketone is neutral, this is neutral, but if you put the litmus paper in the same container, you are going to have some unreacted MnO4. You're going to have some unreacted H plus sitting in there. So how do you know this red litmus paper turning, or sorry, the blue litmus paper turning red is because of the carboxylic acid, or is because of the H plus that's still sitting in there? You don't know. Okay, so that's not a valid test. So don't think that you can do it like this, because if you did that, they will mark you wrong, because it doesn't show understanding. Okay, so this is where the Lucas test comes quite handy. So yeah, that's one thing that you could do. Now, something else that I haven't covered everything. If you have an alkene, sometimes you can use MnO4 minus. You can use MnO4 minus H plus. This will give you diol. Alkene will turn into a diol, and this will go from orange. This will go from purple to colorless. Okay, or if you use MnO4 minus neutral, this will go from purple to brown. Okay, so you're gonna make a brown, you're gonna make brown MnO2, but you don't need to know that. Okay, so that's normally the distinguishing test, and there are some that you probably notice, like say, how do I know what an ester looks like? Ester doesn't do you can't distinguish ester quite easily, but ester tend to have a fruity smell. Okay, so we're using smell, our sense, to distinguish it. Normally have a fruity smell. And amine, and trust me, if you smelled amine, you will know it's amine. It's one of the, you just think of dead fish. If you have some rotten dead fish, or that smell, that's absolutely disgusting. Okay, so if you don't like something, that does chemistry, get them to breathe in some amine, and that's gonna make them remember that smell for the rest of their life. Okay, so amine have that fishy, rotten smell, and then the carboxylic acid, just think of vinegar. But you can distinguish vinegar and carboxylic acid quite easily. Okay, But yeah, this is all the distinguishing tests. You know, you got your alkenes, alkynes, bromine water, carboxylic acid with Lim's paper carbonate, your aldehydes with the Tollens or Benedict solution, your primary, secondary, tertiary alcohol with the Lucas test, your amines with Lim's paper. So, and then you have the solubility test. You have the acyl chloride with water reagent. So normally the really difficult ones to distinguish is ester and amide, and even haloalkane, but they can be processed through the process of elimination. Okay, and then if you can just be very careful that you don't talk about, you know, like what I said here with this red litmus paper test, that doesn't work, and don't use, and a lot of people do this, they think they see aldehyde and they straight away use, if they do aldehyde versus ketone, and if you use MnO4- /H+, this will be marked wrong straight away, because the stronger oxidant can actually react with something like a ketone. Not necessarily something you learn in high school, but they actually do react. That's why we introduce the likes of Tollens reagents and Benedict solution, etc., etc. Okay, so that's all I have for this particular video. Hopefully this helps. I know it's a bit rushed, but you know, and this is where you just need to understand it, grind through some questions, and hopefully that will help. All right, sweet. I'll see you guys next time. Bye bye.